super excited today. I've got Chris from Speed of Air Pistons. We're going to talk about his piston technology, and we're going to try to find out if there's a kink in the armor, but I got a feeling we're going to find no kinks. You were a Top Gun trainer?
So I flew in the Marines, was a fighter pilot in the United States Marine Corps for 24 years.
Wow.
And I was a Harrier pilot, the jump jets, right?
Yeah.
And flew with the British Royal Navy for 3 years. I did a tour up at Fallon, where the home of Top Gun school, was an instructor up there. Flew F-16s, F-18s up there, so yeah, it's good times.
I'm taking the boys. We're going to Miami Formula One. We leave Thursday to Friday, so we're big speed freaks. Come on, an F-16, is there anything more like just like make you feel alive than to hit that thing?
No, it's amazing. Yeah, it's the most fun you can have with your clothes on, I guess.
So tell us, Chris, how did you come to own this business? You know, be the CEO of it, and the journey. Tell me a little about it.
Yeah, great. For me, I retired from the Marine Corps after 24 years. Wasn't sure what I was going to do. I knew I didn't want to go fly commercial. I wanted to go from a Formula One driver to a school bus driver. So I didn't want to go commercial aviation.
Yeah.
I didn't want to do anything with the government. I just wanted to get out and do something sort of entrepreneurial. And Caterpillar came calling. So I went and worked for Caterpillar for a few years. And I rebuilt a facility in Reno, Nevada, or remanufacturing facility. So rebuilt engines and torque converters and transmissions and final drive assemblies and the rest of it. So I rebuilt that. I did like a $30 million renovation and expansion of that business. And during that time, I was introduced to Speed of Air. It was a small R&D company based in Reno. They just had a research lab. That's all they were doing. And one of my clients, Newmont Gold, which is one of the largest gold mining companies in the world, are having issues with the 3516 Caterpillar engines. They were carbon packing. So you had carbon that was packing up in the ringlands, upper ringlands, they're breaking rings. So best case you're placing a cylinder pack on a 3516, 69-liter mine haul truck engine. Worst case is you ventilated the motor through contingent damage. And they came to me and said, hey, this company's got this engine technology, we think it might help, would you build an engine? I said, sure. So we built two engines. We built an A engine and a B engine, same arrangement number, same ECM flash, identical. And one had Speed of Air pistons in it, the dimple pistons, the other one was just Caterpillar OE pistons, and we ran it for 27 months, 18,000 hours, and it was stunning. It was absolutely stunning. So we reduced the soot in the oil by 55% on the engine.
That was not with a gapless second ring, right?
No, that was just a dimple piston.
Same ring pack, just
Yes.
different piston. Okay.
Yep.
Wow. Okay, cool.
And actually it was an OE piston. We just applied the dimple pattern to the OE piston, and we put a thermal barrier coating on the crown of it. So other than that, there were no other modifications to the piston. But we reduced soot in the oil by 55%. So the effect in it was, in those engines, they change the oil by condition monitoring, right? They do oil sampling. So the average oil change in that fleet of trucks at that mine site, this is Phoenix mine site in Carlin, Nevada, was about 250 hours between oil changes. Now this is a truck that's being utilized at about 20 hours a day on average. So 250 hours comes up pretty quickly.
Yeah.
And there's 89 gallons of DEO and 4 Donaldson filters that have to be changed every 250 hours. The Speed of Air truck went to 500 hours between oil changes. They doubled it.
Wow.
And the only reason it got doubled is because Caterpillar says you change the oil based on the condition of the oil, but under no circumstances do you exceed 500 hours. That was an artificial limit applied by Caterpillar. Otherwise, it would have gone even more. We don't know.
Yeah.
We don't know. At the end of life, after 27 months, the maintenance superintendent came and told me, he goes, when we did the tear down the engine, he goes, man, you saved me $180,000 in oil changes over the life of this engine. Wow. One engine.
Whoa.
One engine.
One engine. Crazy. So if you think about 89 gallons of fluid, the man hours, what, 4 or 5 man hours up in the shop, the downtime, and you got a truck that's producing maybe $25,000 an hour in production. So when it's not in the dirt working, it's not making the money.
And every time somebody touches, this is another thing a lot of people never consider. Every time you put hands on something and open something up, you could be introducing an error. A guy could not get, cross-thread something, not get the filter on right. Anytime you got a guy touching a vehicle, there is a possibility that you've added a problem to it. Even something as simple as changing out the oil.
Yeah.
So
100%.
when you don't have to have a vehicle in the shop for maintenance, that's not a bad thing.
Yeah.
So how long ago was that? When was that test done?
2017.
Wow.
And that was when that's when I sort of got introduced to the company. So you asked me how I got involved with it, and that was my introduction. I had nothing to do with speed of air at the time. And again, they were doing research and development, and they were messing around with turbos and heads and intake runners and everything else. It just so happened that they did the piston. And so if you look at the patents and look at and again, all this technology is now patented. We own 3 US patents, an international patent, and have a couple more pending. But the pistons seem to be, 80% of the technology, or 80% of the benefit of the technology, if you applied everything you could to the ICE, sort of resolved around the piston. And of course, that's convenient for us because a piston is a consumable item at rebuild. It's not something we reuse, like say a head.
Right.
And so, just to fast forward, I got involved, and I was fascinated with the company, the technology. I understood kind of the physics and what was going on in there. And my background is doing operational test pilot stuff and taking things and applying it to the real world kind of resonated with me. And they really didn't have a commercialization plan. Like, how are we going to take this to the market? And you got a new technology, you're breaking into a highly regulated industry.
Right, emission standards.
Oh yeah, there's a whole lot of stuff. We started this process, and we started very grassroots. We don't have a marketing firm or sales force or anything else. It's everything we've sold to this point so far has been word of mouth. And just one happy customer saying, hey, this worked. This is what I got. And so we went back and did a lot of significant amount of testing and verification and understanding the physics and what's going on to get people all the time, I'll just drop some ball bearings in there, it'll work. Well, maybe not. That might not work out so well. Yeah, it might not work out so well for you.
That's not how you want to dimple your pistons, man.
Yeah. So, today we have the nuclear physicist from Sandia National Laboratories, Dr. Sal Rodriguez, on the team. We call him Dr. Dimple. He's dimpling hypersonic rockets. He's doing nuclear plenums for the government. And he has figured out how to optimize the dimpling patterns and predict where they need to go and where they're placed. And he's literally written the book on computational fluid dynamics. So other PhDs that want to learn how to do computational fluid dynamics, they read Dr. Sal's book on how to do it. So now we can simulate. We can take a combustion chamber and we can simulate the effects in combustion. And you can say, hey, I want a 6.7 Cummins, apply a pattern to it. And we can do that predictively. Up until this point, our founder and the co-inventor of the technology, Joe Malfin, he's still with us as a technical director, and you got to talk to Joe sometime. He's forgotten more about engines than I'll ever know in my entire life. He's an absolutely amazing mechanic, was a global training guy for Porsche, just phenomenal. But he did a lot of flow bench testing back in the day and doing the design work, but it takes a tremendous amount of time to come up with a dimple pattern design that works and is optimized. And now with the computing power we have today, we can come up and figure this out in real short order, yeah.
We're talking mostly diesel motors up to this point.
Yeah.
Direct injection, gas, port injected.
So
you seeing some of the benefits that you're having here too?
So actually this started in gasoline engines. One of the co-inventors, I said Joey Malfa, and he was doing V-twin motorcycles, Indian motorcycles. There's probably 1,000 Indian motorcycles around the world with dimple pistons in them. Yeah, that's where it started.
Give me the decade.
So this is probably 20 years ago when they started tinkering with this stuff.
Now I heard something, World War II or something like that.
Yeah. So actually there's a docent at the Air Museum in Duxford, England. And a
docent is a plane?
No, docent, the guy that gives the tours around the museums.
Okay.
Museum docent, yes. Or new word of the day, docent.
He wasn't paying attention. I dropped out of college.
So anyhow, guys like, oh yeah, we were messing around these, and like I think the Spitfires or something like that. I don't know what application, but people come up from time to time and say, yeah, I remember NASCAR was messing around with this back in the 70s or the 80s or something like that. So it's not new. I mean, people have been playing with internal parts and dimples and other things like that with varying successes, right? Some people say, oh yeah, we did that, it worked. And somebody else said, yeah, I tried that, it didn't work. Well, the issue is, think about a dimple on a piston. Right, you got a bunch of dimples. How many variations are there? It's infinite.
Infinite.
It's literally infinite. Because the variables are what? The number of dimples,
size, depth,
the diameter, location, the placement. Right. So if you take all those variables, you have an infinite number of applications or patterns that you can come up there. Right. And so some will work a little bit, some will work a lot, and it's figuring out how. So when somebody says, I just randomly put some dimples on there and it didn't work, I'm like, well, okay. And then you think about a piston, the structure of a piston, right? You look on the other, we have oil galleys and things like that. So putting a dimple randomly on the crown of a piston may cause some structural issues.
Yeah.
So there's a lot of design work that goes into it, and a lot of engineering goes into where we put them and how they go there.
What about different motor application, like bigger industrial power plants and things like that? I mean, do you offer, pistons ready to go in that, or where is your major market share?
When we started the commercialization process, we started with the mid-duty diesel. So your Duramax, Power Strokes. We kind of went back to basics, and we focused on diesel not because diesel works. In fact, some of our most successful applications have been gas. We've done methanol, methane, landfill gas, just full of, nasty siloxane. We've done obviously diesel, compressed natural gas, and petrol. And it works in all gasolines. But if you think about, again, a business, industry runs on diesel, and the bigger applications we get into, the better the benefit. Let me back up a little bit. When I started the company, I told our folks, I said, we're not going to be a solution in search of a problem. We're here, just like you are. When a customer comes in, a customer has a problem, and you're here to solve that problem, okay? And usually it resolves in fixing an automobile.
Right.
So our customers come to us with all kinds of problems. We have these in dragsters, Procom dragsters. His problem is I need to get down the track a little bit faster. So we put him in a dragster. He picked up 1700s and 3 miles an hour on an 8th-mile track. Significant.
It's a big time with just a piston change.
Right, so with just a piston change.
Wow, yeah.
So his problem is I need to go faster. I need to win another race. If you're an over-the-road trucker, your problem is fuel's the largest overhead of your business.
Fuel mileage and maintenance.
So if I can give him another mile to gallon, that's solving his problem. Caterpillar, or the Newmont gold mine, when they came to us, it was carbon packing up in ringlands, soot, right? And we can talk about that a little bit, about what that is and how we resolve that. But that was their issue. They're making money hand over fist, but they can't make money if they're breaking piston rings with carbon packing.
Right.
And so when we started the business, we said, look, every industry has their own set of problems. If you're in an EPA non-attainment area in the Permian Basin of West Texas doing natural gas compression stations, and you're getting fined because you can't meet emission standards, that's your problem. So going and talking about more horsepower is it going to resonate with them. So this quarter, here in this month actually, we're releasing our B-twin motorcycles for Harleys and Indians. We're just about finished up with our Euro testing, so the 2.0 TDIs and 1.9 Volkswagens, the Audis,
wow,
the M57s, M47 BMWs, OM 606s, Mercedes, all those applications are coming out.
The question that's coming up in my head, and a lot of people are EGR, exhaust gas, the soot that we're recirculating, you just stick a hose from your butt to your mouth and suck that all day long. Basically what we're asking these medium duty diesels to do all the time, nobody's doing oil sampling or anything like that, so I guess my question is there an avenue, is this an avenue, and you have got access to SEMA benches, where we can get EPA approval on stuff, is this an access to reduce those particulates and maybe reduce these EGR coolers and how much we're doing? Because man, I think as engine builders, doing as many diesels as we do, that's the killer. That's what's killing these motors. You don't see that on motors that ain't got EGR, exhaust gas recirculators on them. What's your thinking of that?
So that's a great question, and actually that's what Speed of Air was founded on. It was all about emissions to begin with. The happy discovery was that by cleaning up emissions, you get more power and torque and you get better fuel consumption. Ever since the Clean Air Act in the 1970s, the automotive industry's answer to cleaning up exhaust emissions has been aftergas.
Aftergas.
Right?
Yeah.
Put a catalytic converter. Your 1978 Duster or whatever had a catalytic converter on the back of it.
Well, the whole world runs on that. We call it aftergas. The medical community does that. We're all overweight, diabetic. We fix the problem after we have the accident. We're not putting all the money and the effort into prevention.
Yeah.
And that's what I'm asking. This is kind of that preventive model, right?
Yeah, and so that's really what it started off. And so you look at, and I call it the 3-letter alphabet soup of aftergas, especially on a diesel engine. About 2005, it was the first sort of emissions control that showed up. You said it.
Yeah.
EGR.
EGR.
Right. So exhaust gas recirculation, and that was developed to reduce NOx. So NOx is created by heat. Right? We get very hot temperatures, we produce NOx. And
most of your NOx happens in the ringland, the top ringland at the edge of the piston.
Right. Right. And so what happens is, so they let's cool the exhaust stream and we reduce NOx, but what's that produce? Soot.
Soot.
100%.
Yeah. Garbage.
So now we have particulate matter, PM2.5, which is a carcinogen, which is harmful to humans, and that's the black smoke that you see coming out of the tailpipe. So then what do? We put a DPF on there. And now we need urea, and we need SCR.
Right, that's what it's
all. So it's like a game of whack-a-mole. We chase one constituent, and another one pops up.
This is our healthcare.
Right.
It's
100%.
It's the exact same thing in our healthcare.
100%. 100%.
So this is your solution
to
get it at the start instead of...
Yeah, so Speed of Air went back and said, you know, there's got to be a better way. Let's go back and look inside the combustion chamber. And if you look at the internal combustion engine, the combustion chamber hasn't really changed in 100 years. We've changed valve geometry, injectors, how we introduce fuel and ignition, but the actual, you got a slug and you got a cylinder. And it goes up and down and makes compression.
Right.
That geometry hasn't changed very much. And so we really started looking at that. And when you start getting it, and this is where you get into the mad science, right? Into the boundary layer physics of what's going on inside a combustion chamber. We understand squish and swirl and tumble. And those are gross movements inside the combustion chamber. So we understand that we need to mix. But what does an engine need to make power? We need a fuel source. We need oxygen. We need air. We need an ignition source. And to convert that chemical energy into mechanical energy, we need compression. Lake Speed Jr.'s got he did a great lecture on, you know, fuel's the enemy of your engine, right? Yeah. And people think, oh, fuel, you light it off and it burns. Well, it doesn't burn.
No.
It doesn't burn. Yeah, I remember when I was a kid hanging around a race car shop, and I was about 15 years old, the mechanic would take a cigarette and he'd chuck it in a can of gas.
And everybody
would run.
Nothing happened.
Nothing's going to happen. It's like, no, it doesn't necessarily burn. All that black carbon that's on that piston right there, what is that?
Unburned fuel?
It's unburnt fuel.
Yeah.
It's carbonized fuel.
And when you say unburned fuel, let's say it this way: it's no gain, no gain,
right?
Loss opportunity.
So when you see the guy rolling coal down the highway, that is unburnt hydrocarbons rolling out the smokestack.
Gail Banks talks about that. About, you know, that's garbage. It's doing you no good.
That's a lot of lost power.
Yeah, 100%. Yeah, 100%. So the idea was, how do we burn it inside the combustion chamber? And we can tell, and just like your medical analogy, you go to the doctor and he wants to know, you pee in a cup, you take his blood sample, 99% of what's going on in your body he can figure out without ever seeing you, just by analyzing what's coming out of your body.
Your biochemistry.
And so we can examine the exhaust of an internal combustion engine, and we can examine the oil of an internal combustion engine, and we can tell you pretty much everything that's going on. And we can see it, we can smell it, we can hear it, we can feel it. So when that Duramax came in there, you heard it was quiet.
Stuck his face in the exhaust.
Yeah, you can. So we
smell different. Didn't smell at all.
You know, people say, well, how's it smoother and quieter? How does that work? Well, think about a 1970, I don't know, pick an engine, diesel engine.
The old Volkswagen Rabbit, a little 4-cylinder 1.8 diesel, man, mechanical injected, noisy.
What did that sound like?
Clackety, clackety, clackety.
Yeah, now you get a L5P or something, you know, modern diesel engine with piezoelectric injectors, and it's quiet. Why? It's a more efficient combustion process. How are we, you know, in those old mechanical injectors, we're just jumping fuel in there. It's like bang, bang, bang,
one
bang.
Stroke, man. You get one shot of fuel.
And now we're able to atomize it very, very carefully, right?
Under 30,000 PSI instead of 2,500.
It's smoother.
Yeah. Right.
So that's because the combustion event that's happening is smoother. And we can look at the oil, we can measure the exhaust, and we can tell what's going on with the engine. So when we have inefficient combustion, this is what we get. We get black carbon packed up on the piston crowns. We can see black smoke coming out of there, and we can see soot in the oil as it passes the rings, but it's also an abrasive, and it wears out the engine. So it affects longevity of your engine life as well. So again, going back to your question about the pistons and what Speed of Air did. So how do we get into dimples? That's probably a really good question. So think about air is a fluid, okay? Yeah. It's like water. Subsonically, until we hit supersonic speeds, it's a non-compressible fluid, and that's how we treat it. Anytime a fluid like air hits a boundary, whether it's a wing of an aircraft, a golf ball, or the crown of a piston, it creates a boundary layer. And that boundary layer is sort of immovable air. There's nothing happening in there. It's static. And so think in terms of the combustion event. If we have this layer of static air over the top of the crown of the piston, and we have a fuel air mixture, we have a flame front that's advancing through that fuel air mixture, at some point it hits that boundary layer, that becomes unburnt, and that fuel is able to fall out of suspension and coat the top of the piston. That's exactly how that's happening. And what the dimples...
There's no turbulence there.
There's no turbulence on the surface.
Gotcha.
So again, when we talk about swirl and tumble, those are big movements, but that's not happening on the boundary. What the dimples do, just like a golf ball, if you go out and hit a golf ball, you go take a ping pong ball, hit that with your golf club. It looks like a wounded duck. It's not going anywhere. It's just going to corkscrew all over the place.
My golf ball still does.
It's because it's not breaking up that, it's not twirling in that air.
Right. So what happens is those dimples on a golf ball, what happens is that boundary layer, just like a wing of an aircraft, as it forms around that golf ball, around that sphere, inside those dimples creates a very turbulent, and that allows that boundary layer to become very thin and tightly bound to the sphere as it flies. So in the case of a dimple on a piston, instead of this thick laminar boundary layer, it now becomes very, very thin and very, very turbulent. So you can think of that boundary layer as unburnt space, unburnt volume inside the combustion chamber. And all we've done is taken that and made that very tightly bound, very turbulent boundary layer. The flame front is able to advance all the way down to the piston crown and burn it all. That's it.
So you take these two motors, like the one you were talking about at the mining, is their carbon buildup is quite substantially less on the top of your piston?
They sprayed down with some brake clean, wiped it down with a rag. It looked like a shiny nickel at 10,000 hours.
Wow.
There was
a lot of question is what the pistons look like after.
Yeah. In fact, if you go on our website, you can go on our website and go to our results page. We have the Newmont report. You can actually see the valves, the pistons, the rings.
We'll put a link up on that on the website.
At teardown
Yeah.
at 18,000 hours.
Wow.
Yeah.
That's awesome.
I mean, we wash these pistons and it still leaves residue.
Oh
on
yeah,
it.
that carbon does not come off easy.
Yeah.
Yeah.
Burn onto the piston.
Right. One of the questions that a lot of our followers have, they're skeptics about the ceramic or thermal barrier. It's going to flake off, it's going to then be ingested through the engine, and it's going to ruin it. Would you mind explaining?
So first off, Cerakote, they make our thermal barrier coating for us. And we worked hand in hand with them, so it's proprietary. It is the best thermal coating on the planet. And I'm telling you, we've tested, this is NASA level stuff that we're using. And Cerakote has been an absolutely fantastic partner, technology partner for us in making this. So there's a couple of things that the thermal coating does. One, it prevents thermal soaking of the piston. Aluminum has a very high heat transfer rate. So if you put a heat source on the crown of the piston and measure the temperature at the bottom of the piston, it's going to be about the same, right?
Yeah.
And so all that heat in the combustion chamber soaks through an aluminum piston, it gets down the oil, gets in the bearings, it causes other problems. The first reason we use it as a thermal barrier, so we prevent that heat. We have taken our coating and done destructive testing. We're about to put a video out, and we're getting 1,000 degrees of temperature delta. We put an IR barometer on the top of it, measure temperature, and put one right at the bottom. 1,000 degrees of temperature delta.
Whoa.
So aluminum's going to melt at around 800 degrees-ish. It starts bubbling.
It gets weird.
Yeah. So we'll get about 1,800 degrees on the crown of the piston.
Wow.
The surface temperature here before the substrate just melts underneath the coating.
Holy.
So it is super, super durable. But the other thing we're doing is heat is work, right? Heat is energy.
Yeah.
People there's a lot of, well, you're lowering EGTs and how are you creating power? Don't understand that part. We're actually reflecting heat back into the turbo. One is preventing the heat to soak through into the oil. The other one is also reflecting energy back into the turbo where it can produce mechanical work.
So let's talk about that. One of the things, the claim is that it reduces EGTs a couple hundred degrees. Now, if you're pushing that heat for work back into the exhaust stream, how are we getting lower?
Great question. This is probably the best question you can ask. We're seeing EGTs reduce about 200 degrees.
That boggles the mind.
Now, is that across the board of all the applications like Duramax, Power Stroke?
Yep,
so
100%.
Roughly.
Isaac Fisher Motor Works is doing, he's got two M57 BMWs right now seeing the same thing, 200 degree EGT drops. So the first thing about EGTs is everybody in the automotive industry understands EGTs because that's what we have. In the aircraft world, I got an airplane. We've got these pistons in an airplane and I fly it. I put my kids in that airplane. We look at EGTs, but we mostly look at CHT, cylinder head temperatures.
Yeah.
Cylinder head temperature is telling you a lot more about what's going on in the combustion chamber of the EGT. Remember, EGT is just 1 in 4, right? You're only getting 25% of the information. So it's on that exhaust stroke is when you're getting that pulse and measuring that temperature. CHT is constant. Secondly is, how are we reducing temperatures at the exhaust? Well, what is causing super high EGTs? Unburned fuel, right? It's just going out.
Right.
So when we see that, so if that's not happening, if you're burning it in the combustion chamber, then that's going to reduce it. But here's what's really cool. The dimples are what's causing the biggest reduction in EGTs. So if we have a dimple, right, and we have airflow over this dimple, there's a downwash flow that goes in, and there's an impingement flow that comes in here as this air recirculates through there. So think about a wing. Wing looks kind of like that, sort of flat in the bottom, and we have air molecules that go over the wing, and the ones that go over the top of the wing have to go faster than the ones at the bottom of the wing, right? Because they got further distance to go. And so that velocity increase creates a low pressure, which creates lift.
Yeah.
Right? On any concavity, we would have the same effect. So this air molecule that's got to go zipping down through here has to go a lot faster than this guy up at top. Well, the math is, and if you ask Dr. Sal, he'd tell you it's 2.7 times more air going across the bottom of that dimple. So this region right here becomes a very high heat transfer region, and it's just sucking heat.
It's a vacuum, basically.
It's just sucking heat out of there. So it's actually, you've got 2.7 times more air moving through those dimples. The other thing is we've actually increased the surface area of the piston. On this piston right here is somewhere around 15 or 20% increase in surface area. On some designs, it's up as high as 40%. So there's a lot going on physics-wise, thermodynamically, that's actually more interesting than the fluid dynamics or the airflow going inside the engine with the dimples. So each of those dimples has a very high heat transfer region in there. There's a lot more air that's flowing over them, and that's how we're getting those EGTs down.
Okay, I got even a better question. Everybody wants to know this. Is there a possibility the federal government comes out with a regulation? By this year, we want you to hit this mark. So then the engineers at GM or Cummins or whatever say, well, this is how we're going to have to do it. We're just going to have to put restrictive crap on all this stuff. You have access to EPA benches where you can test this stuff, and if you meet a certain standard, can we just get rid of that stuff?
Yes, possibly.
Because that would be like the holy grail of diesel.
These pistons right here, our Duramax pistons, are the first piston in the world to be EPA certified. We've just gone through about 6 months at the SEMA garage doing EPA certification of the pistons. The results have been just absolutely tremendous. The follow-up to that will be to get a CARB executive order number, and then we'll expand into our Cummins. Basically, we hope by the end of the year we'll have EPA clearance for every 4-stroke diesel on the road.
But then, can we then take that and then say, now let's run it without the EGR?
Right, so we are taking an LOY Duramax, we're putting a speed of air engine in it. It has EGR on it, but it doesn't have any aftergas on it.
Right.
Our goal is to make that 2015 CARB compliant.
Without the
Tier 4 compliant, without any aftergas. Yeah. Okay. That's the goal. We don't know that we'll get there with just the pistons. We also, Speed of Air owns patents for some turbo technology. We may end up changing the turbo. We're probably going to reflash the ECM. We may need some light substrate on the back end to get it into that compliance, but if we can do it without EGR and DPF and SCR.
That's like hunting with a rifle, man. You don't want to hunt with a shotgun.
Yeah.
You want to hunt with a rifle.
Some of the best engines, I mean, the Caterpillar C15, the 3406E, the 60 Series Detroits, phenomenal engines. And if you talk to these truck drivers, they'd kill to keep those engines. You can't drive them in California, they're illegal. And our goal would be to take, say, a Cat C15. And Caterpillar got out of the truck engine business because they couldn't make them emissions compliant.
Yeah.
We think we can get there. So that's what we're actually working on now, is to come up and get a CARB executive order number for a Tier 4 upgrade kit. So you just buy an upgrade kit. You get pistons, you get an in-frame rebuild kit, you get a turbo, you get a new ECM, whatever we need on the back end to clean it up, put it on your truck, and you're good to go. And legal in California. How the politics work out and all that, we'll see.
Yeah.
They're going to want about 2,000, 2,500 hours of actual lab dyno testing. So that's a big build. So we're doing the LOIs, a proof of concept, just to prove that we can actually take a pre-emissions diesel engine and make it 2024 compliant.
Wow, that'd be awesome.
Some people just want that benefit with the gas prices and everything going on.
Yeah.
I mean, what's the typical average increase in fuel economy?
It's laying out at 20%.
That boggles the mind, man.
Yeah.
Especially for over the road. I mean, that's their biggest expense. fuel costs.
So we got our over-the-road applications. We got guys running against C15s, 60 Series Detroits. They're picking up a mile to the gallon.
It basically pays for itself for the upgrade. I mean, you could do the math here real quick, but the difference between our Monster engine and then a Monster with the speed of air piston, you're like 3 or 4 tanks. You bought your pistons. You bought the difference in piston, in that alone.
Yeah.
Well, in that alone, and then on top of that, how about that dang DPF?
You're probably reducing the amount of times that it regens.
That's what I'm talking about.
Yeah. The first thing they noticed actually on the modern trucks, and including that SEMA truck, the LML, was they quit putting DEF fluid in it. Not completely, but it was just like it just drastically decreased. Oh my gosh, it just quit burning DEF, and the active regen activity went down considerably. Again, if you're not dumping soot into the DPF,
it doesn't need to do its job.
We did a little video down at SEMA. So we built a bypass right off the turbo downpipe. So we were able to test at the tailpipe, but we also wanted to test straight out of the engine. And so SEMA did all their testing of the tailpipe, and then we repeated it all again. We did it with the stock engine, and we did it with the speed of air engine. The average opacity was 26%. So the California limit is 20%. So just to give you an idea, it was at 26%. 26% is black.
Yeah, okay.
Okay. So we're talking about opacity. That's a percentage of black smoke that's coming out of there. So on the stock engine, it was 26%. We did it with the speed of air engine. It looked like a Prius. It was 2% opacity. Straight off the turbo, no aftergas whatsoever.
So a stock engine, 26%. The speed of air engine, and the only change was the pistons.
The only change.
The air filter, no tuning.
Nothing.
No nothing.
All you people,
2%.
there's hope out there. There's hope
Yeah.
that we can get away from this. I've been in this industry so long to see what they've gone to. I know when we went through the 1980s, it was, and if you didn't work on cars in the 1980s, you have no idea what I'm talking about. But there was 1 million vacuum hoses with dash pots to run everything to try to get emissions down. And I mean, you pop a hood on a Honda Accord in the mid 1980s, because I mean, I'm not kidding you, there'd be 100 different vacuum lines coming off there. And that was between carburation and then electronic carburetors to fuel injection. It was for the emissions. And I think we're going through the same thing now. We got all this crap bolted to motors, but we need to go back and look at how we're actually burning that fuel. Yeah. This addresses it at the source, the combustion process.
Another question. So the torque increase as well. So you decrease emissions by a drastic amount. You increase fuel economy by 20%. So decrease emissions, increase fuel economy, but then you pick up power, immense amount of torque in these, right?
Right. So think about the combustion event itself, right? There's 3 sort of direct variables from a combustion event. One is going to be fuel consumption, one is going to be what goes out the exhaust stack, and one is going to be what chemical energy has been converted to mechanical energy, so horsepower and torque. If we fundamentally change the combustion event, then those 3 variables are going to change as well, equally. If we see a reduction in fuel economy, we're going to see an increase in power for the same given amount of fuel, and we're going to see a reduction in emissions because we're converting more chemical energy into mechanical energy inside the combustion chamber. So yeah, where we see it though is not so much on the top end. So for example, the 100% wide open throttle torque sweep, it picked up maybe 35 foot-pounds of torque and about the same number of horsepower, but that's not where you drive your vehicle. When you loaded it in 4th gear, so you had basically a 1-to-1 ratio and ran it, we picked up 200 something,
220 or something.
Like 250.
We thought it was a typo.
I thought this can't, their graphs are off. I think it went from like 250 to 500.
Yeah, so we picked up like over 200 foot-pounds of torque at around 60 miles per hour, which is where you drive the truck. Yeah. And that goes back to fuel economy too. So torque is, people talk about horsepower and diesels, we talk about torque. Torque is what gets you down the road, right? So to get the amount of torque that you need to produce 65 miles an hour down the highway requires a specific throttle position, right?
Right.
If I'm making torque, move that torque cord to the left, that throttle position now changes to get that same amount of torque. Right. Back to the fuel economy.
Less fuel.
And so we're seeing it at the lower end, and that's been really, really consistent. Now that was an exceptional, 250-ish foot-pounds of torque increase at the low end is extraordinary. We were blown away when we saw it. Yeah. But the lowest we've seen is probably around 100 foot-pounds of torque.
Okay, last question. not a bad thing we found yet. Not one kink in the armor of this. What is the kink in the armor? That's a tough question. Is there?
So admittedly, the pistons aren't cheap.
I wouldn't call that a kink.
Yeah, but we.
What you pay for it.
Well,
Yeah,
it pays for itself.
Yeah.
Right.
It gives you money back.
So that's kind of the corporate motto. It's the only piston in the world that pays you back, right? It pays for itself.
Yeah.
We do a lot of work. There's a lot of work that goes into these pistons. The computational fluid dynamics to do the designs is extraordinarily expensive. So it's not as simple as just put it on a CNC machine or lathe and make some dimples. The inspection process. Every one of these pistons, every piston that comes in a black box, not 1 in 10, 1 in 100, every single one sits in a temperature control room at exactly 70 degrees Fahrenheit for 24 hours. Every piston is measured and blueprinted. So you're truly getting a custom set of pistons.
Look at this.
These are all handwritten by a tech.
Yeah.
Right.
Wow. That's very
I've
impressive.
never gotten one of these with another set of.
Well, he's answered my question.
So we do that, and then even the packaging, you know.
Yeah.
I mean,
I have a hard time throwing these boxes away when I'm done with this.
I know.
So it's like a jewelry box, you know, these pistons
Yeah.
are protected.
Yeah.
You know, they're not rattling around in a cardboard box. So we really go overboard with trying to put out the best quality product that the industry can provide. So, you know, you're truly getting a custom set of pistons. But at the end of the day, they pay for themselves. And
Yep.
if there's, and the pricing strategy for us has always been on a return on investment. If you're not getting your money back, look, if a high school kid with this 1995 5.912 valve came in and said, I want to spend my life savings on a set of pistons, and he drives 5,000 miles a year, he's not the customer, right? But if you're a service truck, if you're a tow truck, if you're a hotshot driver, if you're putting 50,000 miles a year in your truck and you're getting 20% fuel gains, the economics, it makes sense quick.
Yeah. Chris, it's a beautiful product. I appreciate you taking the time to stop in and visit with us today.
And
Yeah, it's been a pleasure.
educate us on it. You
Yeah.
answered some great questions.
This is awesome. Thank you very, very much.
Yeah, thanks, Dave. Pleasure being here. Thanks.
Thanks, Chris. Thank you.
All right.